In this problem, we're solving number 656, Smith and Van Ness, 8th edition. Here we have hydrogen sulfide gas is being compressed from an initial state of 400 K in 5 bar to a final state of 600 K in 25 bar. And they want us to calculate the change in enthalpy and the change in entropy. So I got our preliminaries up here, a little diagram of what our initial and final states, 400K 5 bar, 600K 25 bar. And just to give you a little bit of background information, this is all extra stuff for you, but sometimes I think it helps you to realize that even though some of these calculations may seem tedious and it may seem like they're not worth much other than just getting a grade on, some of these calculations do have some importance in real life. Hydrogen sulfide is used especially in the manufacture of paper, and there's some other uses for it. You can look through here. I've given you some safety information as well. One thing I want you to realize, though, is the structure of this structure looks very similar to water, right? And we just did some problems with steam where we emphasized that water is especially in the vapor phase, of course, is a non-ideal gas because of its dipole moment and the hydrogen bonding. And so hydrogen sulfide is very similar in structure, has a dipole moment, and can form hydrogen bonds. So due to the high pressure and the structure that we're dealing with, we can't treat this as just an ideal gas and calculate delta H as Cp delta T and delta S as Cp log of T2 over T1 minus R log of P2 over P1. So what we're going to have to do then is we're going to have to use the residual values. We want to calculate the change in entropy and enthalpy for a real problem. The thing is that for a real gas case, the thing is we do not have extensive property tables for hydrogen sulfide like we do for water. And so what we're going to have to use is we're going to have to use equations of state and heat capacity data to do this. And remember, this is one of the main goals that we had in our lecture notes for chapter 6. So your textbook has the information for equation of state. They also have heat capacity data in the back. You should also realize that there's probably plenty of other sources, and in fact maybe even there's some more extensive property tables for hydrogen sulfide. I did about a 2-minute search and couldn't find any as far as something equivalent to the steam tables, but you can also search and make sure you're using reputable sites and make sure you're careful about the units that are being used. So we're going to use the algorithm that's given in your text for residual properties. And so if you remember what we covered in lecture, here's our T1 and P1, and we're going to go to T2 and P2 for this real process. Well, we cannot do this calculation all by itself, but remember that enthalpy and entropy are state functions. And so I have this written down for, and the graphics aren't good. MathCAD doesn't do graphics very well, especially the older versions, but we're starting at T1, P1, and you can follow along. Your book also has some diagrams of this. We're going to first take this, since it's a state function, path doesn't matter. We're going to first go to this hypothetical ideal gas state at the same T1 and P1. This is purely hypothetical. Then we're going to do our temperature and pressure change to T2 and P2 as an ideal gas. So we'll be able to calculate delta H, delta S for an ideal gas. And then we're going to, at T2 and P2, we're going to go back up to the from an ideal gas to a real gas. And so because it is a state function, delta H for this real process is equal to minus H1R plus delta H for the ideal gas plus H2R. Because remember, residual is real minus ideal gas. So this is a positive H2R this is ideal gas minus real, so that's why we have a negative sign for the H1R there. So as we mentioned in our previous problem, when we're doing residual properties, we have several choices for the calculation method. Number one, we could use a graphical solutions, and your book has a couple graphs, but I wouldn't use this. I doubt there's you would be able to find anything that is easy to use. You can also use tables with the Lee-Kessler correlation, so HR naught, HR1, SR naught, SR1, and we did that. That's a perfectly fine way to do this calculation, but as we found out for the other problem with steam, we had to do a lot of interpolations. We had to interpolate 4 times for these 4 values, and that's just kind of a pain to do. The last method that we looked at was using the Viral equation of state with the generalized correlations, and this was the simplest method computationally, shortest, and if I were you, I would use that. So the first thing that we need to do is, when we're using generalized correlations, is we need to assemble our properties. So we've got the molecular weight. I think we're going to keep everything on a mole basis here, but if we wanted to change to kilograms or a mass basis, we could. And then we have our critical constants. The next thing we do for these kinds of problems is we calculate our reduced variables. So our reduced temperature and our reduced pressure. So I'm calling them T1R and P1R, and then T2R and P2R. And so you can see these are our variables, and you can see right away that if we were to use the Lee-Kessler tables, we would have to interpolate every time. So that's a good reason not to use those tables. We also need heat capacity data for the ideal gas state to calculate delta H and delta S. And this is covered in chapter 4. We skip most of chapter. We skip chapter 4 for the most part. And so far in quizzes and exams, whenever we've had a heat capacity, I've always said that heat capacity is constant, and that's been because doing the calculations with just a calculator, it's still pretty tedious to deal with heat capacity being this polynomial function of temperature. This problem does not give us a heat capacity, and so what they are expecting us to do is they're expecting us to calculate an average heat capacity that's going to be valid over the temperature range that we are encountering. And so what I wanted to do here is just in case your book is not that clear in how these calculations are done. So I wanted to go through these calculations at least once with you so that you can see how it's done. And we're going to look at example 4.2 in your textbook, where we take methane from 260 to 600 degrees C, and we want to calculate the delta H for that process. So we convert everything to Kelvin, our temperatures to Kelvin, and then we go to our table. I believe it's table C1, where we look up the parameters for A, B, C, and D. And one of the things you'll notice is that your table does not give you any units. I don't know why they did this. I think that's pretty awful, but anyway, you are going to have to, if you want MathCAD to work right, you're going to have to supply the units. The other thing that you'll notice is whenever your book does these calculations, they don't include any units either. And I'm not sure why they do that. That's just bad practice. I think you should always include units. MathCAD makes it easy to do that, so you might as well do that. So for A is going to have no units. B is going, and the way you can think of this is, I wrote this equation. Here's your equation up here. But just move the R over to the other side, so divide by R. So CP over R, that's going to be dimensionless, no dimensions. So that means A is going to have no dimensions. B is going to have, and here you can just see, B is going to have dimensions of 1 over temperature to give us no dimensions. C is going to have 1 over temperature squared. And then D is going to have units of temperature squared. The other thing to make sure you're careful about is the exponents. Look over the table, look over the values in the table, and make sure that you put the right exponents. Here for methane, we have B and C, so we have the exponents here. We don't have, D is equal to 0 for this particular compound, so there's no units here. But in our hydrogen sulfide, we'll have C equals 0 and D equals something, and so we'll cover that. All right, so we write we put our constants down, our coefficient values down, and we put the right units on there to make sure that we're dimensionally consistent when we do these calculations. And if you ever use any other source, make sure you're careful. Some of these might use Celsius, and so that will be a difference. The next thing that I do is this is extra. But if you look in your table, you'll find that they do a, if you look in, again, as table C1, you'll see that after Tmax column, they have a column labeled CPIG at 298 divided by R. And what that is, that's a heat capacity at 298 Kelvin divided by R. And so what I'm doing here is I'm just checking to make sure that I have my units right. Now, I should, but you know, everyone makes mistakes, and it's good to check. So what I've got here is I just take this equation up here, excuse me, rewrite it, and it will, with the values of A, B, C, and D, and then I do the calculation, CP over R, so I can just move the divide by R here, and it should be dimensionless, right? And so that's the first check to make sure that you've got the dimensions right. And then we look for methane, and we see a value of 4.217. Here we get 4.216, so we're correct to about 4 significant digits. So this gives me confidence that even though I haven't done a lot of these calculations, the notation in your book is kind of confusing. I've got things right. So now I can proceed. So still within this example of methane, I can calculate the delta H. So this is a delta H that they're asking for in this example. And so that equation is given to you. It is equation, I believe, 4.8 in your textbook. That is 4.8. This equation is delta H is equal to Cp, the integral of Cp dt, where they have integrated this, and they've done some simplification, you can see, to deal with the exponents. And we do the integration, and we can get this in line here, and we get the right answer. So that checks with the solution in the book. That just gives me the confidence, since I haven't done this calculation yet before in MathCAD, and it's kind of a confusing equation to enter, that I've done everything correctly so far. So hopefully we can now go back to our hydrogen sulfide case and start actually solving the problem. So the first thing I'm going to do is I'm going to calculate the delta H and the delta S for the ideal gas step. So that is going to be, I'm not going to calculate the residuals yet. I'm going to calculate delta H and delta S for the ideal gas. So the first thing we do is we look up our heat capacity constants from table C1. And so again, put the units in. This time C is equal to 0, but we have a D term. And so the entry in that table, if you look at the column heading, is 10 to the minus 5 times D. And so whatever that number is, minus 0.232, we have to multiply that by 10 to the 5th. And of course, keep our units. Now what I'm going to do, just to make sure, again, I'm double checking just to make sure that I've entered everything in here correctly before I have to go through all these big formulas. I'm going to set the temperature to 298, and I'm going to calculate the heat capacity at 298 using this equation with these constants. If I take the heat capacity divided by R, I should get a dimensionless number, which is equal to the value that's in that table. It should be 4.4114, and that checks. So again, that's not required. This is just something that I'm doing because I want to make sure that I'm doing things correctly before I go too much farther. So now I can calculate the delta H for the ideal gas step. And so we can use this equation that I showed you above, this equation 4.8. And again, it's going to take you a while to type it in, no matter what method you're using, or even if you're using a calculator. But remember, this is the integrated form of the equation. I've multiplied through by R, because remember, this entire term is going to be dimensionless. This entire term is going to have dimensions. It's going to have dimensions of temperature. And so multiplying through by R will give you dimensions of joules per mole. And we get a delta H of about 7.6 kilojoules per mole. So just remember, this is our ideal gas case where we have to integrate CP over our temperature range. If I had given you a constant heat capacity, it would have just been an easy peasy calculation. Delta H is equal to CP delta T. All right, so now let's go ahead and calculate the delta S for the ideal gas state as well. And again, heat capacity is not constant. And so what we're going to have to do is we're going to have to do the integration for CP over R. Your book does that for you. So this is equation 510. Your book does that integration for you, so you don't have to do it by hand. I suppose you could let MathCAD do it. And so that is given to you in equation 511, and that is this equation right here. The equation 511 will have, let me look this up here. Equation 511 is only the integral, though, for the heat capacity. It doesn't include the pressure difference, the log P2 over P1. So to get the delta S, remember, you have to include, we do have a pressure difference, and so there is going to be that term there. And so we plug all those numbers in, and we get a delta S of about 2.0 joules per mole Kelvin. So now we have the delta S and the delta H for the ideal gas state. Our next step is going to be to calculate the residuals. And so remember, for the residuals, for these residuals, we're going to use a viral equation form. And so we're going to start, I've got a bunch of information here that we can put in. We've already gone through these calculations with steam, so I'm not going to spend a lot of time doing it. But I've got my temperatures, my pressures, my reduced temperature, my reduced pressure listed here. Also notice that MathCAD, when I did this example for the methane, I used a T1 and T2. That changed the T1 and T2 from up above. And so I have to redefine T1 and T2. I did this up here for the delta H and delta S. I kind of skipped over that. So that's one common mistake that people make in MathCAD, is that they sometimes rename variables and forget about it. So anyway, we've got all that settled. So now we do the B0, B1, dB0, dB1 calculations, and then from there we can calculate, we use the equations in chapter 6 to calculate your H1R and S1R. And so again, if you were using the Lee-Kessler tables, you have to do 4 different interpolations to get it, but here we just solve these equations. So these are the residuals. This is the residual values for the for state 1. So going from the real gas state to the ideal gas state. We then do the same calculation for state 2. For state 2, we're at T2 and P2. So we have our reduced temperature, pressure. We get new values for B0, dB0, B1, dB1, and then we simply use the same formula just with the different state conditions plugged in, and we get our HR and SR at those conditions. And then finally we put everything together into our final calculation for delta H for the real process. So you remember that's going to be delta H for the ideal gas minus H1R plus H2R. And delta S for the real process is going to be delta S for the ideal gas state minus S1R plus S2R. And these are the answers that we get. If you were to look in the publisher solutions, you would find that the answers are slightly different from what we got here. I've gone over this and I don't see any mistakes. If you guys see any mistakes, let me know. But these are the answers that we get. The publisher solutions, one of the reasons why I do not like the publisher solutions is they show zero work. They show none of the intermediate calculation steps. And so it's really tough to troubleshoot whether they went wrong or I went wrong. But I believe everything in here is correct in using the tables. And so this pretty much finishes up the subjects that we have covered in Chapter 6, where we've taken a process and have gone from the ideal gas state the real state to the ideal gas, do the ideal gas change, then go back up to the real state to get the actual delta H. And we did this using only heat capacity data and equation of state information. So that's, if you think about it, that's kind of nice. That's pretty impressive that we can do this. There are other problems in your textbook where, for example, throttling processes or isenthalpic processes where T2 is not known, and where you have to do an iterative calculation for these calculations. But those are a little more complicated than I think we want to get into. I just want to make sure that you understand the basics of how these calculations are done and that you can apply them to a well-defined process like a compression process, a throttling process, or a turbine expander process.